This short video tutorial, I will go through the lab FEA simulation of torsional stresses and displacements. You can download the lab manual basically from your D2L by going into the required section and for week 9 contents. There is also a part file available there. So if you want, you can modify the part file that is already there to create your own part file, or you can do it from the scratch like I will just demonstrate it to you. So this has all the detail of the task that you need to perform and also the data for each of the students. So I will be performing the task based on the following data. That is a torque of 360 Newton meter with the AISI 1020 steel shaft with a diameter of 30 mm and a length of 600 mm. Your data is different, so make sure you check your student ID and then correspondingly choose the right material as well as the loading torque and the shaft diameter and length. So with this, you can then perform the same operations as I am doing, as I will be doing in this video, and then you can actually produce your own report. Make sure you complete all the sections of this report. You provide all the hand calculations as well as the finite element results. So the shaft in question is a typical shaft like the one that we solved in the class. So this is the schematic representation of that shaft. It is being fixed from from the one end, and it is free from the other end. And in this shaft, the torque being applied is 360 Newton in my case, and in your case, you will choose the actual value that is given in your table. So firstly, what you need to do is you need to do the hand calculations. And in my case, I've done these numbers over here, and I'll quickly go through this. I've already explained this procedure in the class as well. So the input torque for me is 369 Newton meters because I am keeping all the other units in megapascal. So I will convert this into Newton millimeters. So this becomes 360 to 10 to power 3 Newton millimeter. The diameter of the shaft is 30 millimeter, which means that the radius is 15 millimeter, and the length of my shaft is 60 mm. Once I plug in these numbers over here in the formula, in the torsional stress formula, I will be able to calculate the value of the stress. But for that, I will first need to calculate the value of the J, which is here. So the J value is given by the formula 1 over 2 pi r4. This is also included in your formula sheet. So polar moment of inertia of this shaft. So this is half pi into 15 raised to power 4 in my case, which becomes 79,521. When you substitute all of these values in this formula, you get the value of the maximum shear stress 67.9 megapascals. Now keep this in mind as I explained earlier. The above formula calculates the value of the shear stress in r theta coordinates. So this is the value which is here on all of this outer periphery of the shaft. So this tau max, whether you measure it on this location or this location, is the same, and it is 67.9 megapascal. Later on, when we perform the finite element analysis, the analysis will be carried out in the default coordinate system, which is the Cartesian coordinate system. So we will need to convert those values because those numbers will be different along this periphery. So we will need to convert those numbers to match these numbers. So we'll have to basically do a conversion of the coordinate system. Then, as far as the angle of twist is concerned, that can be simply found from the value from the formula TL over JG, like we discussed in last section. Again, the value of torque in this case is 360 for me, and into 10 to the power 3. 316 to 10 to the power 3 for my case, but your case you need to consult the table. 600 mm is the length of the shaft. 7952 is the moment of inertia, which is J, for moment of inertia of the shaft, and the value of G is basically the shear modulus. Now this value of shear modulus can be read from the SolidWorks, but what I suggest that instead of directly reading this value from the data card in the SolidWorks, you should read the value of the Young modulus E as well as the Poisson ratio from SolidWorks, and then use those numbers over here to calculate the value of G. This will result in a value which is slightly different from the one shown in the data card of the SolidWorks, but it is the value which SolidWorks internally uses for its calculation. The difference is only slight for ductile materials, but for one of the choices of the material that I've given, which is over here, that is gray cast iron or other brittle materials. This difference in the value reported on the data card and the value that the SolidWorks actually uses is significant. So I again recommend that you use the value of Young modulus and the Poisson ratio to calculate the value of the G for theoretical calculation. Now, how you are going to get that from SolidWorks? So let me just quickly open SolidWorks up. So I have SolidWorks 2023 installed on my machine, but you may have 2025 version as well. There is not a lot of difference between these versions for the task at hand. There may be differences in other advanced features, but for the task that we are going to perform, there's not a lot of difference. So I'm just going to create an empty part file right now, which I will later on amend. Right now, I just want to show you how to actually check the material properties. So if you click on this material tab and click on edit material, you'll get here the list of the materials that are there. So in my case, it is AI Psi 1020 steel. And if you go here, and I've already chosen the value as in megapascal. So if I look here, so my value of elastic modulus which is E, is 200,000 and Poisson ratio is 0.29. The shear modulus here is given as approximately 77,000, and once I plug in the numbers in my formula, I get a value which is close to that, but not exactly same as that. So I will actually use this value for my hand calculations. So once I plug in these numbers, so I get my angle of twist as 0.03504 radians, and when I multiply this with 180 divided with pi to get the value of the angle of twist in degrees. So this is the value of angle of twist for this particular case. So we will be comparing these two numbers, the angle of twist in degrees as well as the maximum value of the shear stress in the shaft. Now, when we are going to create this model now in SolidWorks, we'll need to make sure that all the boundary conditions are same as those being assumed for our theoretical equations derivation. In real life scenarios, you can have the boundary conditions which are representative of the real world situation, but because we are now trying to compare the theoretical equation with the simulation, so we will try to keep the boundary conditions exactly same. Later on, we can actually change some of these boundary conditions to also have a sort of what if analysis on what if some of the boundary condition changes. Now, the way I will be doing this, I will create the part in front of you, and then we will carry it from there. So I'll choose the system of units is in millimeter grams seconds, so that it's easy for me to draw using a consistent set of units. I will first of all go into the sketch command, and in the sketch command, I will create a circle that I will then later on extrude. I will choose the right plane for this. It is important that you keep with the same coordinate system as me so that the variable naming convention is the same. If you choose a different coordinate system or a different plane, then the components of the stress, for example, x, y, and yz, their meanings will change. So you will have to then make sure that you are using the correct components. So I'll do it on the right plane, and I will actually create the circle with a center. So I will manually adjust these values. So I will actually put this on the center, and for the radius, I'll choose the value of 15 millimeters. So 15 millimeters is the value that I am going to choose. So this is, I will now add a smart dimension just to make sure that the value of the diameter is correct. So you can see here that it is 30 mm, which is the one that I want. Once I'm happy with this, I'll click on this tick mark, and now I can actually exit my sketch, and I can actually go on to the features pane, and I can click on extrude boss to basically extrude the shaft along the x-axis. So I need this to be 600 long for my case. In your case, you have the value as I think 500 for most of the students, but make sure you check the actual data in the data provided to you. So once I click, then I got my shaft, which is over here. So this is the main shaft. So I'll just call it as main shaft. This is the single part, so really it does not matter too much if you don't change the name. I will at this stage also add a reference axis. This reference axis will help me in terms of defining the top basically direction. So I'll create a reference axis for this shaft, which is shown here now. So I'll just select OK. Now with the shaft ready, I can actually uh, basically create the simulation. So for that, I can go into the simulation tab and I'll go into the new study tab over here. And in the new study tab, I will now give it a study name. This is a static study that we are carrying out. So this is the same as the one that we used in the last lab as well. The reason being that in this course, most of the work that we are carrying out is based on principles of static, and we are assuming the body to be in equilibrium. So with this, I can now give it a name. So I'll just call it as Shaft Fall 2025 as my study name, and I'll call it as fully constrained to indicate the boundary condition. So fully fixed. So I'll later on explain the difference between this and the other boundary condition. So I'll click here, and now I've got my part which has been transferred here, and I can now actually start creating my I can start applying my material, then the boundary conditions, then the load, then the meshing, and then the creation of the final part. I will stop this video over here so that the videos are not too long and I can have them as a multiple part uploaded separately.